All right, gang, here we go. This is for Chem 2, Unit 11. We're going to talk about different other kinds of titration. Specifically, we're going to talk about what happens when you start combining weak acids with your strong, or weak acids or weak bases with the strong acid or base opposite of. Anyway, okay, so last video we talked about what it looks like if you have a strong acid titrated with a strong base or vice versa, and it made this nice, cool looking curve that just kind of went up and then shot across and was nice and parallel and symmetrical on both sides, right? And then so this was starting with an acid and then titrating to a base, and then base going with an acid would go the opposite direction. All right, weak acid though with strong base, this looks a little bit different. We're going to start off acidic, same way, okay? But when we start adding our base, we're going to start increasing, and we're going to increase a little bit more. All right, and then we're going to raise up. Notice here, now this is the big kicker that's different between your strong acid, strong base titration and a weak strong titration, is that your equivalence point is no longer at 7. For a strong titration, your equivalence point is always at 7. However, for a weak strong, all right, your equivalence point is going to be at a different spot, and we'll talk about how to calculate that here in a minute. All right, now, and then afterwards you'll go back up and then figure out your concentration. So this is kind of what's in solution at these different points. So this is titrating acetic acid with what looks like sodium hydroxide. All right, so when you're in this first region here, you have just acetic acid. So in order to find the pH here, it would just be a simple Ka problem. Okay, simple Ka problem. You just set up your ice table, so on and so forth. All right, once you start adding sodium hydroxide, you're going to start neutralizing this acetic acid. Now remember, one of the ways we could make a buffer was by adding a strong base to a weak acid. So while we are adding the strong base, if we haven't completely neutralized that acid, then this acid will be turned into its conjugate, and then therefore we will form a buffer solution. So when we're in this area right here, we call this the buffer region. Okay, buffer region. All right, and that makes sense because this is the region where our pH just isn't changing very much. Like, it's changing quite a bit here, right? But our pH, isn't changing too terribly much. So this is called the buffer region. And so when we're in that buffer region, we can use the Henderson-Hasselbalch equation. All right, we'll put HH for Henderson-Hasselbalch equation. All right, now once we've reached our equivalence point, remember our equivalence point is when the moles of the acid are equal to the moles of the base. So once we've added just as many moles of hydroxide as there were hydronium to start with, we are at the equivalence point. Now notice here that we actually have a basic solution, and it's really interesting why this would be. The idea here is that our acetic acid, that's our CH3, COOH, when it gets neutralized, it's going to turn into, it's going to get neutralized by that hydroxide here. I should probably have added that hydroxide in there, huh? Here, let's get rid of that. We'll come back here. So we're going to add in this hydroxide, OH minus, all right, and this is going to form water, okay, and then, is my face in the way? Not yet, okay, and then acetic acid, CH3COO minus acetate. All right, so this is what we're going to form, right, once our reaction is all complete. All right, and so when because this is a strong base, this reaction is going to go to completion. So at the equivalence point, we won't have any acetic acid left or hydroxide left. All we'll have left is just this stuff over here, our water, which is just part of our solution. That's just our solvent. That's no big deal. And then our acetate. Well, acetate is a weak base. So if we have acetate in our solution, it's going to act like a base, and therefore we'll actually have our KB reaction, right? So we'll have our acetate acting like a base, COO minus plus H2O, okay? And because it's a weak base, it'll actually create hydroxide. All right, and form this new equilibrium because we started with this. And so now at the equivalence point, this turns into a KB problem, okay? Because all of our acetic acid turned into our acetate. Now, if you started with a weak base and titrated with a strong acid, you'd have the opposite. This would be a KB problem, and this would be a Ka problem. After the equivalence point, though, it doesn't matter what the concentration of the acetate is because it's a weak base where you have excess strong base. So this guy just turns into a strong base problem. We'll call that SB. All right, so when you first start, it's a Ka problem. during the buffer region, you use Henderson-Hasselbalch. At the equivalence point, it's a Kb problem, and then after the equivalence point, it's a strong base problem. All right. Oops, wrong way. All right. And so as more base is added, the pH level's up, and this is the exact same for strong acids. So let's see. So a strong base, let's just draw this out real quick. If we started with a strong base and titrated it with, so here's our pH, okay, and we're titrating it as milliliters of whatever our acid is, strong acid. That's added. So as this is added, we're going to start off here at some, relatively high pH, and then we're going to come down, okay, level off, and then it'll drop down, and then we'll have some concentration. So this isn't my best curve ever, but here's our equivalence point, all right? Here's our equivalence point. Equivalence point, all right? Here's our equivalence point, and this equivalence point is going to be slightly acidic. So here's 7 right here. All right, and notice that we were slightly basic. Okay, we're adding base. We get this buffer region. So at the start right here, this would be a Kb problem. Okay, if we're starting here before we add any of our titrant, we have a Kb problem. Within here, okay, we call this a buffer problem, right? This is our buffer region. It's just in the basic side. So we use the Henderson-Hasselbalch equation. At the equivalence point, we only have weak acid in there, so this would be a Ka problem. And then after this, all of this would be a strong acid problem. Easy peasy. Okay? So what does this look like? These are just your general steps. So you've got a solution containing a weak acid. You're adding a strong base. All right? This is a neutralization reaction. You've got your weak acid with your strong base, and it's going to form your anion and your water. All right? Once you get those guys there, you can calculate your new values of HA and A minus at equilibrium, and then you can use your Ka to calculate it, or you can use the Henderson-Hasselbalch equation. All right, so that's how you would do it if you calculated, if you had only neutralized some of your weak acid. So this is really what is in the buffer region. All right, so these are your steps if you're trying to solve it within the buffer region. All right, so so this is just a way of looking at, well, how is this different than a strong acid titration? Okay, and we've already kind of pointed out a lot of these. The weak acid titration will always start at a higher pH, and that makes sense because weak acids are weaker than strong acids. Okay, and so we're always going to start out at a higher pH. So notice that even if we have a relatively high Ka value, we're still at a higher pH than the strong acid was. All right, the pH change near the equivalence point is always smaller for the weak acid. All right, and that's because of that buffer region. This buffer region kind of slows down the pH change. All right, here, look how sharp this changes for the equivalence point. Here, these guys, that change is a lot smaller. And then the pH equivalence at the point is always greater than 7 when you have a weak acid, and less than 7 when you have a weak base. All right, now, just to change gears real quick, and then we'll do some practice problems. We've got to talk about indicators. Indicators, we're going to bring this up now, is because what essentially they are is a buffer solution or a weak acid conjugate base solution. And the cool thing about them is that the weak acid and its conjugate have different colors. Okay, and so as you shift that equilibrium from one side to the next, you actually have the solution changing color. And so this indicator just is purely dependent upon the Ka of the solution. Okay, so each indicator has its own pH range over which it changes color. All right. And so we've got, like here, we've got phenolphthalein, and its color changes around 9. So below 8, it's completely clear, and above 10, it's pretty dang purple and pinkish. And then here around 9, we get this nice color change. Methyl red, above 6, it's orange. All right, and then below that, it's like this weird red color. Okay, and so its color change happens in here around 5-ish. All right, so we can use these indicators to help us choose where we think this equivalence point is going to be. All right, and so we can use the indicator to find the equivalence point in a titration as long as its color change is in the same region where the pH rapidly changes. Okay, so if we know that we're titrating a weak base with a strong acid, we need to make sure we choose something like methyl red, because methyl red will change color below 7. Okay, and then if you're titrating like a weak acid with a strong base, you would start somewhere up here, because you know that's about where it, you know that the equivalence point is going to be somewhere above 7. Okay, and so here they're just kind of showing you a couple of different graphs here. Here they're saying that this phenolphthalein would be a good choice for this one because its pH change, or its color change, excuse me, is about where the equivalence point would be. Methyl red would not be a good choice for this one because its color changes way down here. You wouldn't be able to use the indicator to tell you where your color is because it would turn yellow over here, and then you wouldn't have any idea where your equivalence point was. So you always need to make sure you use the indicator that's best for your option here. All right. Opposite way here is when we started with a weak base and conjugated with a strong acid. We wouldn't want to use phenolphthalein because phenolphthalein turns pink and purple up here, or goes from purple to clear at about around 9. But we know because it's a weak base strong acid titration that our pH is going to be lower than 7 at the equivalence point. And so therefore our pH is good. We need an indicator that changes color down here like methyl red. Okay. Now, titrations of polyprotic acids. Okay, polyprotic acids, remember, are acids that have more than one H to give away. All right. Now, and essentially what this amounts is if you're going to titrate a polyprotic acid, then what happens is you'll have more than one equivalence point. You'll have an equivalence point for each hydrogen that comes off. Okay, so here's your starting point. First hydrogen is being titrated and it comes off, and so this would be your first equivalence point right here. And then your second hydration comes off, or a second hydrogen comes off, and there's your second equivalence point. And so depending on how many hydrogens can come off, you're going to have that many equivalence points. Okay, so something like citric acid is triprotic, and so citric acid would have 3 equivalence points if you titrated it. So like Gatorade has citric acid in it. So if you were titrating that and using a pH probe in order to find the equivalence point of that guy, then you would see 3 distinct humps like this. All right, but something like sulfuric acid, it has 2. Because it's diprotic, all right? Carbonic acid is diprotic, so it would have 2. All right, now the other interesting thing is that if we use the Henderson-Hasselbalch equation, okay, we know that so the Henderson-Hasselbalch equation says that the pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. Right? That's what the Henderson-Hasselbalch equation says. So we know that when the base and the acid are equal to each other, this whole thing becomes 0. Right? So essentially, when the base concentration and the acid concentration are equal to one another, the pH equals the pKa. Well, if they're in the same solution, that means their volumes are the same. So really, we're looking for if their moles are the same. So if the moles of the base and the moles of the acid are the same, we get the log of 1, and so the log of 1 is equal to 0. So the pH is equal to pKa. Well, where in our equation or in our graph would that be true? Where would the moles of the base be equal to moles of the acid? Well, that would always be true when we're right at halfway to wherever our equivalence point is. So here and here. All right, so this gives us a really interesting tool is if we have a titration and we know that our titration, we reached our equivalence point at, there's a nice pretty number of 50. If we reach that equivalence point at 50, we know if we find the pH at 25, okay, that's halfway to the equivalence point. If we find the pH at 25, it's like 2 and change, or no, 1 and change, 1.3, 5, or whatever it is, then that's going to be equal to the pKa. And this doesn't just work for for just polyprotic acids. This works for any of our acids here. So we can go back here and look at, this guy here. Halfway to the equivalence point would be 50, okay? And so we could find the pKa of our guy here just by going halfway, so that'd be 25, right? And so we draw this guy over, and so it'd just be slightly above 2. So the pKa of our solution would be like, 2.05 or something like that. And then we could do the same thing with this one. And so this guy, the pKa would be just about 4, 3.98 maybe, or something like that. And then this one, the pKa would be about 6, and this one would be, the pKa would be about 8, all right? Oh, sure. Look at that. I guess. Because if we took the pKa of this, it would be 10 to the negative 8, right? So we just say, I can't believe I didn't put that together on my own before. Because we know that the pKa is equal to the negative log of the Ka. Well, if and so if the Ka is 10 to the minus 8th, that'd be the negative log of 10 to the minus 8th. Well, shoot, that'd just be 8, which is exactly what we got for the pH there. Okay. We could do the same thing for the bases as well. All right. So if we have something like this, it took, again, they keep choosing 50, which is kind of nice, but at the same time, not representative of most reactions. But if we went to 50, all right, then 25 would be here, right, halfway to the equivalence point. So whatever the pH is here, that would be equal to the equivalence point, okay? Or, sorry, yeah, the halfway to the equivalence point would be right here, and that pH would be equal to our pKa. So it's pretty nice, pretty nice. All right, let's do some practice problems here. Okay, so it says, why is the pH at the equivalence point larger than 7, okay, when you titrate a weak acid with a strong base? Well, if we know we're larger than 7, this means that we have a basic solution. So essentially what they're saying is, why is your solution basic at the equivalence point when you have a weak acid and a strong base? Okay, well, we established before that that's because the conjugate base is the only thing left in solution, and that conjugate base is going to act like a base and create hydroxide. So let's see if that's an option. There is excess strong base at the equivalence point. Well, that doesn't make sense because that's the exact opposite definition of the equivalence points. The strong base has to equal the weak acid we started with. All right. There is excess weak acid at the equivalence point. Well, if there is excess weak acid, then you wouldn't be at the equivalence point. And not only that, but if you had excess weak acid, you'd be below 7, not above 7. All right, the conjugate base that is formed at the equivalence point is a strong base. Well, that doesn't make sense. The conjugate base came from a weak acid, so it has to be a weak base. So that one's right out. It can't be C. All right. And says D, the conjugate base that is formed at the equivalence point reacts with water. And that's true. That's what we established earlier. It says this statement is false. The pH is always 7 at the equivalence point in pH titration. That is false. All right. That is only true for a strong. All right. Now it says calculate the pH at the equivalence point when 40 milliliters of 0.025 benzoic acid is titrated with 0.05 molar NaOH. All right, so we're at the equivalence point, so we're going to assume that all of our benzoic acid has been neutralized. So our benzoic acid is going to completely turn into benzoate. So we're going to have 0.025 or all of this benzoic acid we started with is going to be turned into benzoate. All right, so what does that look like? Well, we need to figure out how many moles of benzoic acid we started with so we could figure out how many moles of benzoate we have. Okay, all right, so we got to take our 0.025 moles per liter of our benzoic acid. So we'll call that HBA. All right, just save ourselves some time here. All right, and we're going to multiply that by the volume so we get just the moles. So we'll multiply that by 0.0400 liters. Okay, so we take 0.025 times 0.04, we get 0.001. 0.001, and this would be moles of benzoic acid. So that's how many moles of benzoic acid we started with, and we know since we reached the equivalence point, all of that is going to turn into benzoate. So really we have 0.00100 moles of benzoate. Right, we'll just call that Ba minus. All right, now in order to find the pH we need of this guy, we need to set up a Kb problem. Okay, and so what occurs here is that we have our benzoate. Okay, benzoate is going to react with water. All right, and it's going to form OH minus and then our benzoic acid, HBA. And then we're going to set up our ice table. Well, the thing that goes in ice table is concentrations. So we can't use our moles that we just calculated. We're going to have to use concentration. So that means we got to divide this whole thing by our new volume. Well, the new volume isn't just what we started with. All right. It is the new volume here. So this is kind of tricky, right? So what we've got here is we started with 40 milliliters, so it's definitely at least 0.04, but we're going to have to add in the volume of the NaOH that we added. So this problem is getting more and more complicated as we go. Now, we know here that the sodium hydroxide is twice as concentrated as the benzoic acid. So that means it's going to take half as much sodium hydroxide. So the amount of sodium hydroxide we added would have to be equal to half of the volume we started with. So that would be 20 milliliters or 0.02. All right. So we'll take our 0.001 divided by 0.06. All right. And so our new concentration of our benzoic acid or a benzoate is 0.0167 molar. Okay, so now we're going to take this guy, so that's our initial concentration of our benzoate, 0.0167. All right, and water doesn't matter because it doesn't participate in our equilibrium. Hydroxide ion concentration and benzoic acid are both equal to 0. We're going to lose some amount of this. We're going to gain some amount of this. We're going to gain some amount of this. This becomes 0.0167 minus x, and then x. All right, now this is equal to our Kb, right? So our Kb would be equal to x squared over 0.0167 minus x. But we need our Kb value. So these problems are kind of they're intense, right? So now we got to find our Kb. Well, we know that Ka times the Kb is equal to the Kw. So that means our Kb, maybe I'll do it down here, our Kb is equal to our Kw divided by our Ka. All right, so our Kw is 1 times 10 to the minus 14th. And we're going to divide that by our Ka, which is our 6.3 e to the minus 5th. All right, so we get 1.59. I'll just call it 1.6 times 10 to the minus 10th. All right, thank goodness these two are way far away from each other, so that means we can neglect that x. We can forget about it. 1.6 times 10 to the minus 10th. We'll do some fancy magic, so our x is going to be equal to our 1.6 times 10 to the minus 10th times 0.0167. And then we'll take the square root of that answer. All right, so we get 1.6 times 10 to the minus 6th. That's what I got. All right, so that is our molarity. So that's our x value. That's the concentration of hydroxide. So if we want to find the pH would be equal to the 14, right? Because if we take the negative log of that, that'd be our pOH. So we take the negative log 14 minus the negative log of our guy there, so 1.6 times 10 to the minus 6th. So that means our pH here would be equal to 14 minus the negative log of our answer. And we get 8.21. Right, 2 sig figs, so we go 2 decimal places past the pH there. So 8.21. So that's that to solve for if you calculated the equivalence point starting with a weak acid and adding a strong base to it. All right, let's do the other one here. Okay, so take a screenshot or something, or I guess you could just rewind. All right, I'm going to erase all this so we have room to do our next one here. And it's the same thing, but now we got to work backwards. Okay. Guess I need the Ka or the Kb of NH3. I guess I'll have to Google that. This is taking way too long. This is taking way too long. Way too long. Way too long. This is taking way too long. We'll get there. Anybody know any good jokes? Ooh, I know one. What did the hat say to the hat stand? You stay here. I'll go on ahead. That's like one of my favorite jokes ever. All right, here we go. So 40 milliliters of 0.1 molar NH3 is titrated with 0.1 molar HCl. So these concentrations are equal to each other, which makes it nice. So now we can just assume we know that we added 40 milliliters of that. So we'll just make a note of that because we already thought about it. So we can use that later. All right. So we need to figure out how many moles of NH3 we started with. So we're going to start with our 0.1 molar NH3. All right. And we're going to convert that into moles by multiplying by the liters we added. So 0.0 liters. All right, so we have, well, I don't need a calculator for that, 0.00400 moles of NH3. Okay, and that's going to be turned into its conjugate acid because NH3 acts like a base. All right, so we're going to turn that, so that's just going to turn into 0.00400 moles of NH4 plus. All right, now we know already that we're going to need the concentration, so we might as well divide this by the total volume. Now the total volume is 40 plus 40, or 0.04 plus 0.04. All right, so we say 0.004 divided by 0.08. So our concentration is 0.05. And that makes sense, right? Because we had 0.1 and then we doubled the volume, so we're dividing it by, 1/2, or multiplying it by 1/2, dividing it by 2. So anyway, so we get 0.05. So that's the NH4. Now the NH4, once it's in solution all by its lonesome, it's going to react, and it's going to react with water. All right, and it's going to form NH3 plus H3O plus, right? Because it's going to act like an acid, water's going to act like a base. And so now we get our ice table. Now the initial concentration of the NH4 is 0.05. Water, straight up 0, NH3. Okay, NH3 here. None of that to start, none of that to start. We're going to lose some amount of that. We're going to gain some amount, so 0.05 plus x, and then gain some amount of x, or minus x, and then plus x, and then this will be x and x. All right, so that means our Ka value would be equal to x squared over 0.05 minus x. Okay, now we need the Ka value of ammonium. So they didn't give it to us, so I'm just going to Google it because I don't have a textbook handy. Ka of ammonium. The Ka of ammonium is 5.8 times 10 to the minus 10th. All right, so that's going to be equal to 5.8 times 10 to the minus 10th. All right. Now, these two are way far apart from one another, so we can get rid of that x. So that means our x, going to do some algebra here, our x is going to be equal to 0.05 times our 5.8 times 10 to the minus 10th, 0.05, and then take the square root of that, and I got 5.39 times 10 to the minus 6th. All right, but they want the pH, so we're going to take the negative log of that. So the pH here, pH is equal to the negative log of our guy there, 5.39 times 10 to the minus 6th. And so our pH is equal to, well, how many sig figs? This guy has 3 and 3, but the Ka value I used only had 2, so maybe we should stick with 2. So it would be 5.27. All right, so there's our pH. Cool? Yeah. So lots of stuff. You're really starting to hit the good stuff with chemistry here. Don't worry. This is about as hard as they get. I know I said that in the last video, but you know this is also pretty tough stuff because you got to remember a lot of things that are going on here. You got to remember your Ka, your Kb rules. You got to remember your pH rules. You got to remember how they react with water, and so on and so forth. So this stuff can be pretty difficult to keep track of. So make sure you're really keeping good notes of what things you're doing while you're working the problems. That's the biggest thing. Really think yourself through these steps here. All right. So anyway, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.